This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. In this lecture, we'll discuss the common emitter configuration of transistor and its characteristics. What is common emitter configuration? So, in common emitter configuration, base is the input terminal, collector is the output terminal, and the emitter is a common terminal for both input and output. So that means we need to consider the emitter terminal as a common for both input and output port. So as the emitter terminal is common, we should connect the emitter terminal to the ground, and hence the common emitter configuration is also said to be grounded emitter configuration. So here the common emitter configuration is most commonly used or most widely used transistor configuration because of its advantages. So this is the transistor, NPN transistor, which is connected in common emitter configuration. So emitter terminal is connected common, which is grounded here, and the collector terminal is taken as output terminal, and the base terminal is taken as the, so this is the input and this is the output. That means we need to apply the weak signal whose strength is to be improved between the base and emitter, and the output, that is the amplified version of that weak signal, is to be taken between collector and emitter. So that means VBE is considered to be the input voltage, and VCE, which is the common collector to emitter voltage, that is the voltage between collector and emitter terminal, is considered to be the output voltage. So here actually this voltage is considered to be VBB, whereas this one is VCC. So we need to have in series, always you remember, whenever you are giving some supply, you need to have some resistance in series with that. So here for simplicity purpose, I have not included that, but definitely we should include some series resistance along with the voltage source. So here, as we are connecting voltage source, this VBB is not equal to VBE. That means there is some difference here, and VCC is also not equal to VCE. Because we are connecting some resistor, there will be some voltage drop across that resistance. That you have to remember. So this is a common emitter configuration. How can I, common emitter configuration of NPN transistor. How can I decide this as NPN transistor? Based on the direction of this arrow. As it is coming out, so we have to represent, we have to consider this as NPN transistor. So base is P-type, emitter N-type, collector N-type. So we need to provide the biasing such that, so as I told you that in any of the configuration, in order to perform amplification operation, so emitter to base junction should always be forward biased, and collector to base junction should always be reverse biased. So in order to forward bias this emitter to base junction, so as the base terminal is P-type, so the positive terminal of the battery is connected to P-type, and negative terminal of the battery is connected to N-type emitter. So base to emitter junction is forward biased. This is emitter junction is forward biased. Now coming to this supply. So collector is of N-type. So we need to reverse bias this. So as it is N-type, so what we need to do? Connect the positive terminal of the battery. So this reverse bias the collector junction, and emitter terminal is connected to negative terminal. So here that means as we are connecting the collector terminal to positive collector terminal to the positive terminal of the battery, the remaining terminal will be connected to the ground. So this is the common emitter configuration, and based on that the directions of current, as IE is leaving, so IB and IC are entering, because we all know that IE is equals to IC plus IB. Okay, so these are the conventional current directions I have shown. So this is the transistor version NPN. So this is replaced with the symbol here. This is the common emitter configuration transistor, which is NPN transistor connected in common emitter configuration. So now let us discuss the characteristics of common, before discussing the characteristics of common emitter configuration. So this configuration offers medium input impedance, medium output impedance, and medium current gain and voltage gain, whereas it offers high power gain. So these are the characteristics of common emitter configuration. Whereas common base configuration offers low input impedance, high output impedance, whereas the voltage gain is high, current gain is low. So here, for coming to the common emitter configuration, input and output impedances are medium. Even the current gain is medium and voltage gain is high. Voltage gain is high and even the power gain is also high. So this is the common emitter configuration. NPN transistor, PNP transistor connected in common emitter configuration, and this is NPN transistor connected in common emitter configuration. So here the signal with whose signal strength is to be improved is given to the base and emitter terminal, and the output, which is the amplified signal, is taken from the collector and emitter terminal, which is taken from the collector and emitter terminal. So that means the input signal is applied between base and emitter, and the output signal is taken from collector and emitter. So this is NPN transistor. If you look at the current directions here, as it is PNP, emitter current is entering, so base and collector currents are leaving. Whereas this is NPN transistor, as the emitter current is leaving, so base and collector current are entering. So this is the common emitter configuration of NPN and PNP transistor. Now let us look at the equation, or else the relation between the currents. So as we all know that in common base configuration, this is the equation of collector current in common base configuration. Alpha DC into IE plus ICB naught. Why I have included IDC? Because this is under DC condition with the applied DC voltage. I am not applying any AC voltage. So that is why alpha DC into IE plus ICB naught. And we already know that the relation between emitter current, base current and collector current, that is IE is equals to IC plus IB. So now let us substitute this one in the above equation, that is substitute. Let us consider this as equation 1 and equation 2. Substitute equation 2 in equation 1. Then what I'll get? I'll get IC is equals to alpha DC into in place of IE, I have substituted IC plus IB plus ICB. So if I take, so actually as this is my common emitter configuration. Now let us have a look at, so as we all know that in common emitter configuration, base is the input terminal and collector is the output terminal. So base is the input and collector is the output terminal. So the input parameters will be emitter current is the input current, and the voltage between base current is the input current, and the voltage between base and emitter is considered to be the input voltage. So that is VBE. So IB and VBE are the input parameters, and coming to the output parameters. So as we all know that output is taken from the collector terminal and the emitter terminal. So collector current is considered to be output current, and the voltage between collector and the emitter terminal is considered to be output voltage. So IB and VB are the input parameters, and IC and VCE are the output parameters. So now let us discuss the relationship here. So now what I want to have a relationship between the input current IB and the output current IC. So I have to get a relation between input current IB and the output current IC. That is my aim. So for that I have considered these two equations and I have substituted IE in these above equations so that I have got it. So now I am sending this IC term this side. So then I'll get 1 minus alpha DC into IC plus alpha DC into IB plus ICB. So now here I want IC in terms of IB. IC in terms of IB. So for that what I'm saying, send this term to the other side of equal to symbol. So then IC becomes alpha DC by 1 minus alpha DC into IB plus ICB naught divided by 1 minus alpha DC. So here IC can be written as beta DC into IB plus ICE naught. What is beta DC? So beta DC, I have considered this entire term as beta DC, where beta DC is equals to alpha DC by 1 minus alpha DC. And ICE naught. What is ICE naught? 1 divided by this entire term is considered to be ICE naught. ICB naught by 1 minus alpha DC is nothing but ICE naught. So whereas this can be written as beta DC plus 1. That means 1 by 1 minus alpha DC is equals to beta DC plus 1. This is the relation. So here now, what is this beta DC? Beta DC is nothing but current gain or amplification factor of common emitter configuration. Common emitter configuration. So this is beta DC. So where beta DC is given by alpha DC divided by 1 minus alpha DC. As we all know that alpha is ranging from 0.95 to 0.98. So if I consider alpha is equals to 0.95, what is the beta value? Beta value becomes 0.95 divided by 1 minus 0.95, which is equals to 19. And if I consider alpha is equals to 0.8, then I will get beta is equals to 0.95, and this is 0.98. 0.98 divided by 1 minus 0.98, which is equals to 49. So that means for a small variation from 0.95 to 0.98, it has changed. What is the variation that you can observe? 19 to 49. That means for a small variation in the value of alpha, we can have a large change in the value of beta. That means alpha has a large significance on beta. So that means for a small value, for a small change in the value of alpha, the beta value changes significantly. And here the alpha is approximately equals to 1, where beta is of the order of 100. It always ranges from 50 to some 400. So this is the range of beta. So where beta is nothing but the current amplification factor of common base configuration, or else current gain. So here, when comparing with the alpha, when comparing the alpha and beta value, alpha is very much less than beta. So here, as alpha is very much less than beta, what happens to ICE naught? ICE naught is equals to beta plus 1 into ICB naught. So that means what I can say, ICE naught is also very much greater than ICB naught. So that is the reverse saturation current in common emitter configuration is very high when compared to the reverse saturation current in common base configuration, because it is multiplied by beta DC plus 1, where beta DC is a large value. For example, if I consider this as 99, 99 plus 1 means 100 into ICB naught. 100 into ICB naught. So this is the current relations in common emitter configuration. And now, even if you consider now, for example, so that means IC is equals to beta into IB plus ICE naught. Anyhow, this is also a reverse saturation current. If I consider this reverse saturation current is negligible when comparing with this beta IB, so then IC can be approximated as IB into beta. Then beta can be defined as IC by IB. That means this is the output current, that is IC, and this is the input current in common emitter configuration. That is why what I am calling this beta as current amplification factor or current gain in common emitter configuration. Okay, so this is IC is equals to beta IB. So here now, for example, let us consider IB is the base current which is due to the recombination. So the recombination is only from 2 to 5%. So the beta IB value is very less. It is of the order of microamperes. Let us consider this as 10 microamperes or else 10 milliamperes. And if I consider beta as 100, then what is the value of IC? IC will be equals to, from this equation, beta into IB. So where beta value is 100 into 10, so that is 1000 microamperes. So that means if the value of IB is 110 microamperes, the value of IC is becoming 1000 microamperes. That means the current is increased, output current is increased. So that is why we can say that the common emitter amplifier can be used as current amplifier. Only the common emitter amplifier can be used as a current amplifier, whereas the remaining two configuration, common base and common collector, can be used as voltage amplifiers. So this is about the common emitter configuration and the current relations of common emitter configuration. Okay. So the thing you have to remember is the beta value is very large. It is of the order of 100. That is 50. It ranges from 50 to 100. And for a small change in alpha, the value of beta changes significantly. And the reverse saturation current in common emitter configuration is very high when compared to the reverse saturation current in common base configuration. Now let us discuss the input characteristics of common emitter configuration. So whatever it may be the configuration, always you remember, input characteristic curves are drawn between the input current and the input voltage by keeping the output voltage as constant. So what is the input current here? IB is the input current and VB is the input voltage, whereas the output voltage is VCE. Output voltage is VCE. Keeping VCE constant, we should record the values of VBE and IB, and the graph is to be plotted between VBE and IB by taking VBE on the x-axis and IB on the y-axis. So here again, this emitter to base junction, these are the characteristics drawn between VBE and IB. So again, the emitter junction is forward biased here, and hence the input characteristics of common emitter configuration are also similar to the forward biased PN junction diode characteristics. So this is when VC is equals to 0, the characteristic curve is this. No. What happens if I increase VCE from 0 to some higher value? Again, here the early effect arises. So now what happens? What is the early effect? Early effect means the base width modulation, means due to the increase in the, as I am increasing VCE, what does it mean? It increases the reverse bias at the collector junction. Now due to the early effect, what happens? The depletion layer will more penetrate into the base region, and due to which what happens? The effective width of the base region where the recombination takes place will be reduced. Due to that, what happens? The base current will be reduced. Okay, so due to the early effect, so if I increase the collector VCE, which increases the reverse bias potential at the collector to base junction, and hence the depletion region will penetrate more into the base region, due to which the effective width of the base region where the recombination takes place reduces, and due to that the rate of recombination reduces, and hence IB will be reduced. IB is reduced. So now you all know that the characteristics are drawn between VBE and IB. As I have increased VCE, IB is decreased. So that is why what happens? The characteristic curve will now shift to the right side. Shift to the right side, or else move away from the origin. So here, if you observe the characteristic curve, this is at VCE is equals to 0. If I increase VCE to some higher value, let us consider VCE is 10 volts. So as IB is reduced, the curves will be moving away from the origin. This is also due to early effect, which we have discussed in the common base characteristic, transistor characteristics lecture. So if you have any doubt about that early effect, you just go through that video. So this is the thing is you have to remember is the characteristic curve will be moving away from the origin or towards the right side. So that is about input characteristics. Now coming to the output characteristics. So these are the characteristic curves drawn between the output current and the output voltage by taking input current as constant. Input current IB is constant. So input current IB is constant. So by keeping the input current IB at some constant value, increase the value of VCE and note down the output voltage. Note down the output current and plot the graph between output voltage and output current, taking output current on y-axis and output voltage VCE on x-axis. Initially, IB is considered to be 0. So here, now we all know that the equation of current. What is that equation? So we have seen that the equation of current is IC is equals to beta into IB plus IC E0. So if IB is equals to 0, so then what happens? IC is equals to IC E0. So this is the reverse saturation current. So even there is a current which is flowing due to the minority charge carriers. So here this is cutoff region because we are open circuiting the input junction. Means what? We are reverse biasing the input junction. As both the junctions are reverse bias, again this region is called as cutoff region. So even there is a reverse saturation current ICE0, but it is greater than ICB0 in common base configuration. And now, here if I increase IB, okay, if I increase IB, so then what happens? We are applying some forward voltage to the emitter junction. So as it is forward biased, so it operates in the active region. So here, this is the active region of operation. So, and IC is equals to beta IB plus IC into IC E0. So where beta is very high. So in the previous case, IC is equals to IE, that is in common base configuration, but it is not equal to the input current because it is multiplied by a factor beta. So that means the output current is very much greater than the input current. So if I consider 20 microamperes, I'll get some 200 microamperes or 2000 microamperes of input current. So this is the output current. So this is the region where both the emitter junction is forward biased and emitter junction is forward biased and collector junction is reverse biased. Okay, and this is the region where the both the junctions are forward biased, and hence this acts as a short circuit. And hence it has acts as on switch. So in saturation region, transistor acts as on switch, and in cutoff region, transistor acts as off switch, and in active region, transistor acts as an amplifier. So here, one more thing, we can also have breakdown if you still increase the reverse voltage across the collector to base junction, then the base width becomes 0, I said. So due to what, punch through arises, and hence the breakdown occurs and the current increases rapidly. And one thing you need to remember, the output characteristics of transistor are identical to the reverse bias characteristics of PN junction diode. If you reverse these characteristics, so what are the characteristics of PN junction diode? These are the characteristics of PN junction diode, right? So these are the things that we can, if you reverse this, these will be identical to the PN junction diode reverse bias characteristics. So input characteristics are similar to the forward biased diode forward biased PN junction diode characteristics, whereas the output characteristics are identical to the PN junction diode under reverse bias. Okay, so this is about common emitter configuration output characteristics. And coming to the transfer characteristics. So again, these are the characteristics drawn between the output current and input current, taking the input current on x-axis and output current on y-axis. So as you all know that IC is approximately equals to beta into IB. So again, we have a linear relationship. So if IB increases, IC also increases. And when IB is equals to 0, IC is equals to IC E0. And hence, instead of starting from origin, so it starts from IC E0. This is IC E0. And as IB is increased, IC is also increased. And these are the characteristics drawn by keeping the output voltage as constant. And from this characteristic curve, we can calculate one parameter which is called as current amplification factor or else gain, that is beta. Beta is defined as the ratio of change in output current to the change in input current by keeping the output voltage as constant, that is delta IC by delta IB by at VCE. Okay, the parameters that we can also calculate from the characteristic curves are dynamic input resistance. It is defined as a ratio of input voltage VBE, change in input voltage VBE with respect to the change in input current IB by keeping VCE as constant. And in CE configuration also the input resistance is very low. And coming to the output resistance, it is defined as a ratio of change in output voltage, that is VCE, to the change in output current IC by keeping input current IB as constant, which is given by delta VCE by IC, delta IC, IB as constant, and it offers high input resistance. So that is all about the common emitter configuration, its characteristics, and the various parameters that we can calculate from the common emitter configuration. That's all for this lecture. I hope it is clear to everyone. If you have any queries, you can post it in the chat box, a comment section. You can post your queries in the comment section. Thank you and end.
Like, share and subscribe. Hit the bell icon for more updates.